It was like, I thought you were going to get caught. I was like, somebody told me I couldn't.
To find the critical points of a function, and critical points are items where you have a maximum, a minimum, or maybe a point of inflection. What is a critical point? Points on the graph of a function where the derivative is 0 or does not exist are important to consider in many application problems. F of x is a point. It's a critical point if x is in the domain of the function, and either the derivative of x equals 0 or the derivative of the function x does not exist. At a critical point, the tangent line is vertical, horizontal, or does not exist. Here's an example of what all of that means. You have f of x equals x squared minus 8x minus 10. We want to find the critical points of this function. That's the purpose of this. And remember, critical points can be a maximum point, a minimum point, or a point of inflection where the direction of it is changing. Here you go. Need a smaller marker. There. Step 1 is to find the first derivative. So the first derivative of the function x in this case is going to be 2x minus 8. Now to find the critical points, you're going to have to set that derivative equal to 0. So 2x minus 8 equals 0. And then solve for x. 2x equals 8, and x equals 8 divided by 2, which is 4. Now to find the y value of the critical point, you have to plug this back in to the original equation. So you'll come up with f of 4 is 4 squared minus 8 times 4, and then minus 10. So that's 16 minus 32 minus 10, which is negative 16 minus 10, and that's a negative 26. So you have a critical point at the following coordinate, 4 and then negative 26. Now it's a critical point, but we don't know if it's a maximum, a minimum, or it could be a point of inflection. To test this out, you have to pick numbers on either side of 4 and then plug them back into the derivative to see what happens. You're not plugging it back into the function, you're plugging it back into the derivative. So, our point is 4, and I probably should have changed colors at this point to set some of this apart. So we'll put this as a red 4. There's your 4, and that's not an absolute value sign. That's just showing that 4 is in the center, and now we need points on either side of it. To be certain, when you're that close to 0, choose a negative for that side, and on the right side, choose a positive. Negative 2 and negative 6 did not come from this problem. They came out of thin air. The only reason I chose them was because one is on the left-hand side of 4 and the other one is on the right-hand side. It's your choice. You could have used negative 1 and 5, negative 10, and 4 million. It doesn't matter. Alright, so we're going to test the first part. So on the first part, if I put this negative 2 in for the derivative, and remember the derivative is 2x minus 8. So you'll have 2 times negative 2 minus 8, and that comes out to be a negative 4 minus 8, which is negative 12. Now test the other one. 2 times 6 minus 8, and that's going to come out to be 4. Here's what's important. Not the numbers, but the signs of the result of what you get for evaluating the derivative. And I'll put this in bold ink. You had a negative to start with, and then you ended with a positive. If you start with a negative and you end with a positive, then what you have is a minimum for that critical point. In other words, the graph comes down and then goes back up, and at the very bottom of that bowl, the center is going to be 4, negative 26. And in this case, we only have one critical point because when we went back to solve for x from right here, it's just a simple linear equation, so you just have one value. Your critical point is 4, negative 26. It is a minimum because your combination was minus to start with and then plus to end with, from left to right, when you tested the derivative for the numbers you chose. Now here's an illustration of all of that. Here's the graph of the original function. And notice down here at the bottom, look at that point. That is 4, negative 26. And notice that it is at the very bottom of the graph. It is a minimum value. You can't get any lower on the graph than that. So it does verify what we have done. Here's a cheat sheet to use when you're plugging in values on the first derivative to find out if it's a maximum or a minimum point, or neither. If your sign combination is minus and then plus, I interchange minus and negative all the time. So if it's negative plus, then it's going to be a minimum value. And remember, we're going from left to right. So if the number you chose to the left of the x value that you solved when you set the derivative equal to 0, if that one comes out negative, the second one comes out positive, it's a minimum. If you start with a positive and then have a negative, what your critical point is a maximum point. So in other words, it's going to be upside down. If you started with a positive and ended with a positive, or you started with a negative and ended with a negative, notice that I have bracketed those off together, then yours will be neither a maximum or a minimum. And when you go to look at the graph itself, like we did on the previous screen, more times than not you can figure out it's a point of inflection. Here's an example of a point of inflection. A point of inflection would be something like this, where you have a graph that goes down and then back up like that. The point of inflection would be approximately there. I don't have a graph drawn on this page, it's blank. Notice that a maximum up here would be seen up here, a minimum down here. The point of inflection is there. It's kind of like what cuts that S-curve in half. Example. Here's the function. It's g of t equals t squared plus 2t minus 15. What do we do first? Find the derivative. So we need, and I don't like writing lowercase letters. I know it's a lowercase g, but I'm going to write an uppercase g. The first derivative of g of t is going to be 2t and then plus 2. What do I do after I find the first derivative? Set it equal to 0. So actually that's not an equal sign, but we'll just leave it there. 2t, which is going to be 2t plus 2 equals 0, and that's going to be 2t equals a negative 2, and then divide negative 2 by 2 to get a negative 1. So we're going to have one critical point in this one. What do I do next? Into the derivative?
No, you put into the original.
In the original, yes. So when we do that, I'll change colors here. I wrote a little bit largely on this one. G of negative 1 is negative 1 squared plus 2 times negative 1 minus 15. So that's 1 minus 2 minus 15, which is a negative 1 minus 15. That should be negative 16. So you have a critical point, CP, of negative 1, negative 16. Everybody still with me? Okay, what do I do next? We have to find if it's maximum or minimum, and what do we do to do that? Yes, pick numbers on either side of the x value. We'll go to purple and that is -1. So on the left-hand side of that, you don't have to choose numbers that are outrageous. I think a -2 would do the job, and then on the right side of that, what's on the right side of it that would be an easy number? 0, yeah, so we'll use that. Alright, so if you plug in a -2 where? The derivative, yes. So if you plug that in, you get 2 times -2 and then plus 2. That's a -2 and then plus, or not -2, -4 plus 2 is a -2. And then plug in the 0. 2 times 0 and then plus 2. That should give you a 2. Your sign combinations are the following. You start with a negative and you end with a plus. What kind of critical point is it? A minimum, yes. And we will verify that by looking at the graph of this function. Here is the graph. And remember what the critical point was. It was -116, and it does show up right there. That is the critical point. It is a minimum. Everything is verified on that. On your calculator, if you ever want to verify your stuff, I was going to give you graph paper, but I think some of these are going to end up with windows like X and Y minimums and maximums that even with Zoom 9 and all of that, it still would be much easier to do that than graphing on paper. So on your graphing calculator, you can type in the function and see the graph of it. So if you come up with a minimum value, but you look at the graph and it's actually upside down bold, then chances are you've done something wrong. The first derivative, I'm putting f of x, and it's really d of r, but the first derivative of d of r is -2r minus 2. If you go back and solve -2r minus 2 for 0, or against 0, then it will be -2r equals 2, and then divide 2 by -2, and come up with a value of -1. Did everybody get -1 for that part? Okay, after that, plug it back into the original function, and you'll have d of -1 equals a -1 squared minus 2 times -1 and then plus 8, which has to be squeezed in there at the bottom. Now a -1 squared is 1, but it's negative sign outside, so it's -1. Double negative is plus 2 and then plus 8. -1 plus 2 is 1, plus 8 is 9. Did you get 9 on that one? So the critical point is -1, 9. Now we have to determine if it's a maximum or a minimum. We have a -1. On either side of that, we could choose a -2 and then a 0. If we choose a -2, remember you're plugging it in here, not the original 1. So it's -2 times -2 and then minus 2. 4 minus 2 is 2. And then -2 times 0 minus 2 is minus 2. Notice that your pattern is you start with a plus, you end with a minus. Therefore, this is a maximum point, and we'll take a look at it on the graph before you come up. Here it is on the graph, and remember that the critical point was -1, 9. Is that right? -1, 9. And there it is. It's an upside down curve because of the negative sign that was on the r squared at the beginning of the function. If you start with a negative variable squared, then it's going to turn it upside down. So that's why this is a maximum.